Okay, let's give you guys some more practice. So let's say you've got a laser pointer right here. You're going to fire the laser and it will hit this wall here at this point here. So this is your dots here. When so this here is your theta here. We are going to slowly increase theta. Okay. So initially the laser would be fired. Initially theta would be 0, so it would be horizontal here. Slowly we're going to increase theta. Okay, so slowly we're going to increase theta at a constant angular speed of this. Okay, so we want to use the word speed rather than velocity. You would use angular velocity if you were to rotate it here and then back here. Well, you would want to use angular velocity when you want to take direction into account. But because we're only going in one direction here, it's better to keep things simple and use angular speed. Well, anyway, initially theta will be 0, and then we're going to increase the angle here. So the angular, so this here will be at a constant angular speed of pi over 180 per second. Okay. So the question is, when the pointer, so initially the pointer will be down here, and then as you increase theta, the pointer will move up here. The question is, at a height of 200 meters above the ground, what will be the speed of this dot right at this point here? Okay, so yeah, so what in effect, the speed, the vertical speed is dh by dt. Okay, so we're going to call this h, we're going to call this theta here, and the angular speed is really d theta by dt. So basically you're given this and you want to somehow get this, so you want to find some sort of connection between theta and h here. Okay, well anyway, find out dh by dt, which is the speed of this dot when it's 200 meters above the ground. Something else to bear in mind, when theta gets really big up here, a small increase in the angle would translate to a big vertical distance. So that means when theta is very big, if you increase the angle slightly, the speed of that dot on that wall would be very high. Whereas down here, a small increase here, it would only translate to a small vertical distance. Whereas up here, it would translate to a very big. It would translate to a very big distance here. Okay. Well, it would translate to a very big distance. Well, anyway, find out the speed when it's 200 meters above the ground. Okay, so press pause and have a go. Okay, so to do this here, this here will be h. H here. We're going to call this h. We're going to call this theta here. So we need some sort of connection between theta and h, and that connection is really tan. Okay, the tan this, and well, the connection is tan, and something else to bear in mind. As time goes on, because you want to differentiate this with respect to time later on. As time goes on, if you think about it, as time goes on, theta is a function of time. So when you differentiate it, if you differentiate it and there's a theta in there, you're going to need d theta by dt. And also h, well, as time goes on, h is also a function of time. So bear that in mind, okay, when you differentiate it. Well, anyway, we were at the point where we have theta and h here. We want to find some sort of connection between theta and h, and that connection is tan. Okay, so hang on. So we're given d theta by dt as this. This was given to us initially, but we want to find some sort of connection between theta and h, and that connection is tan. You see, tan theta will be h over 1000. Okay, so now use times both sides by 1000. That will take you to here. Now use implicit differentiation. Don't forget, h is a function of time. H is a function of time, and theta here is also a function of time. So when you come to use implicit differentiation, you would differentiate this, but you need to stick the dh by dt. That's this thing here. Differentiate this. Don't forget, when you differentiate tan, it will give you this. Okay, so that will then take you to here, and because theta is a function of time, you do need theta by dt. Okay, that will then take you to here, and then tidy up. It will give you this, and don't forget, this is what we want to know. This was given to us. This is the angular speed. Initially, it was given to us. So now all that we need is we now need theta. You see, looking at this precise moment in time when it is 200 meters above the ground, because that's what we want to know. We want to know the speed of that dot when it's dead on 200 meters above the ground. So when it's dead on 200 meters above the ground, you need to know this theta here. So when it's 200 meters above the ground, theta here will be this. Okay, so now we know theta. We can put it in there. So hang on. So when it's 200 meters above the ground, the angle will be this. Theta will be this, and the angular speed was given to us as this. So now we want to know this. This here is our angular speed, so we can put this into here. Okay, and theta, when it's down on 200 meters above the ground, theta will be this, so we can put this into theta. Okay, so then it's blah blah blah. dh by dt will be 18.15 meters per second. So what that means is when it's 200 meters above the ground, the vertical speed of this dot, this laser pointer here, this laser point here, will be 18.15 meters per second. Okay.